Hello, my name is Anil Madhavapeddy. I have the perfect follow-on talk to Felipe's excellent talk about XenStore, talking about how we've been rewriting XenStore for a little while. So this is great. I mean, it's actually I agree with everything you said. This is all good news, and this will be a very positive talk. The majority of this work has been done by. Now, can you see the slides? Yep, by Dave Scott from Citrix and Thomas Resinier, who works in my group in Cambridge. And part of this work has been done as part of the MIRAGE project, which is one of the sub-projects of the MIRAGE of the Xen project. And just to give me an idea, how many people here have heard about MIRAGE and know roughly what it is? Great. So okay, that's about half of the room. So I won't go into details about MIRAGE. I just wanted to now, if I can just get the ability to present this thing. Now, all of these slides are actually self-hosted in MIRAGE. So I'm actually presenting this from a little ARM board, which I will not. I will try to lift it up. Why not? All right. Here we have an ARM board, and this is running on Xen ARM, and it is also running a microkernel that has been written using MIRAGE. And all of the slides are centrally hosted on this little thing and not actually being served from the internet. And this is important because the Wi-Fi in the conference is awful. So it's actually quite convenient. Otherwise, we would not have been able to present these slides. But to give you a sense of what's going on, it's about a unikernel, which is a standalone kernel that is not running anything to do with Linux. And it's slightly less than a megabyte in size, and it's entirely written in OCaml. So the idea is that we wanted end-to-end security for everything from the protocol stack all the way down to the device drivers and so on. And the application logic is actually pretty simple. It's just a bit of declarative web server stuff, and the MIRAGE framework takes care of all of the details of doing kernel compilation. So as a programmer, you need to learn OCaml. I find it simpler than C++. But also the framework takes care of all of the details of kernel compilation and Xen kernels and so on. And interestingly, the binaries, since they're just a megabyte in size, are small enough to track directly in Git. So it kind of gives us a transformative way of dealing with deployments and handling all of these big kernels. Now, so this is just a thing in case I couldn't actually bring it up. Now, so one of the things we've been doing in the last year has been working on a second version of MIRAGE, which improves on the prototype we released in 1.0. And there's loads of information, loads of new components in MIRAGE. And I'm not going to cover them in this talk. But some of the big features are, for example, it's one of the first new operating systems to support Xen ARM, and as the self-hosting demo shows. What I'm going to talk about in this talk is a new Git-like storage system that we've been working on, which is called IRMIN. So this is rethinking the way file systems work in this new world. We've also built from scratch a TLS stack, which is kind of our anti-heartbleed. And the idea is that when you deploy these unikernels in the web, of course, you need to support SSL. And so rather than deploying OpenSSL, we've built from scratch all of the libraries, including X509, ASN1, TLS 1.0 in pure OCaml, and link those all the way through our existing OCaml stack in order to give an end-to-end SSL stack. And we're working on formally verifying it and proving that it's actually mathematically correct as well as a faithful implementation of TLS. And also, there's been a bunch of compatibility work, for example, to let us build clusters of unikernels by using the vChan protocol. So we can take not just one little microkernel, but take a cluster of them and let them communicate using the vChan protocol. And also just ways of interacting with C code much more easily, which I won't talk about here. But all of the information for these new features is all up at the website, which is, of course, itself written in MIRAGE. And there's lots of blog posts that you can read offline when you actually get net access. But this talk is all about how we've been using MIRAGE to contribute back to Xen. And specifically how we're working through some of the limitations in the Xen tool stack, particularly in the XENSTORE, and actually giving the XenStore a future in terms of being high performance and actually distributable as well, and hopefully dealing with a number of the issues that our friends at NAC, for example, have found in trying to build very, very dense, scalable systems. And we do even have plans to upstream this stuff. It's been taking a long time, but it's coming together at last. So a quick bit of background before I dive into the XenStore. And what is IRMIN? Now, whenever you build a library operating system, this is one of these standalone unikernels, you don't have a conventional kernel to fall back on, which means we don't have a file system, we don't have any of the usual abstractions that you have inside a POSIX-like operating system. And so we got the opportunity to rethink exactly what this would look like. And what it doesn't look like is ext2. What it does look like is a model that follows a Git-style branching system. So whenever you build a new storage system, we thought, well, we need something that can run user space and kernel space, all of the backend supported by Mirage. And we wanted a key value store. But instead of the key value store being a flat space, because almost anything you do in this new world of distributed systems is always out of sync, well, we thought it would be very nice to implement the basic operations required for distributed systems, which is Git-style branch consistency. Any node can pull, push, and merge with other nodes. And anything you want at a higher level has to be built as a library on top of that. And one of the really, really cool things is that this preserves all of your history by default. So we're making the assumption that we have a lot of storage spare in the short term. So if you're ever in a storage constrained environment, you almost certainly do not want to use this model. But in reality, we have vast amounts of storage available, and particularly in a distributed system, it's a cheap resource. Whereas dealing with the reconciliation and network protocol stuff is actually a very expensive problem. And so in this database, Unikernels version control all of their data and have a distributed provenance graph of everything that's been going on. And this forms the basis for everything I'll talk about. Now, just some basic concepts, you know roughly how it's structured. If you use Git, then Git essentially stores all of the objects, the things you store in the Git database, in something called an object DAG. And this is append only, it's very easy to distribute, and it provides a stable serialization for anything you can throw at it. And importantly, this backend is independent of exactly where you put it. So I just want to have this graph, and I can store that in memory, or I can put it on disk, and I can encrypt it using convergent encryption, or I can just store it in plain text. These are all just options in the library. And interestingly enough, this looks a lot like a heap, except that they're position and architecture independent. Because anything you put into this object store, you take a SHA-1 hash, and therefore you can keep references to other SHA-1 hashes. So instead of memory pointers, we have SHA pointers, which form a graph of all of the things you're putting into the blob store. Then on top of the blob store, we have to build our actual file system abstraction. And we have a history DAG. And what this does is that it's also append only. And it can be persisted into the low-level object store. But crucially, it keeps track of the history of the objects you put into it. So imagine you're building a tree of file system nodes, and anytime you modify it, you create an entirely new tree, and then you make a small change, and you keep an ordered log of all of the changes. And so this is a lot like source code version control, and therefore you maintain an audit log of all of the operations. Crucially, it makes merging these things much easier because whenever you have to merge two distributed nodes, you know the common ancestor of the operations from which they came. So you don't try to merge nodes which are completely independent. You actually try to do a Git-style merge where you can see the common ancestor and where they've diverged, and you can do a much more intelligent merge operation. And you get snapshotting and reverting and so on for free in this system. So just to, it'll be quite hard to see, but the structure is at the low level you have a blob store, which is just a bunch of SHA hashes that you're storing onto some block device. Then you have a DAG of the history operations, which is the source trees. Then you have a bunch of human readable tags, like the head tag that you name to keep track of particular change sets inside there. So this IRMIN takes two forms, if anyone wants to try it. You can just use the OPAM package manager to install a command line interface. And this command line interface implements an in-memory format, so you can just launch it in memory and just play with things without a persistence, or it's got a full implementation of Git. So its actual storage format is a normal Git file system. You can use a Git command line. I'll show you that shortly towards the end of the talk. And similarly, the network protocol can be a custom format, which is very optimized for reconciliation, for example, over vChan, or it can use an HTTP REST, or it can use Git. So you can push, for example, to GitHub or any kind of existing Git store that you have. And the interface is a JSON interface, or more interestingly, from the XENSTORE perspective, it's an OCaml library that you can actually build against directly without having to use a command line. So you can build very efficient ways to manipulate these things from OCaml code. And one of the nice things about OCaml is that it does let you build very complicated data structures. And so we've also built a series of merge-friendly data structures like queues and maps and sets that are designed to be distributed at scale. And also a number of backend implementations like Git and HTTP REST as well. So this is IRMIN. It's just a quick kind of 1,000-line, 1,000-foot view of what's going on, or 1,004-foot view as Lars said earlier. And the reason that we're getting excited about IRMIN is that we wanted to fix XenStore. Now, XenStore is it's a very, very old configuration database in Xen. It's very much like Plan 9. And you notice a few features about XenStore. It runs either in user space or kernel space, just like Mirage. It's got a key value store, just like IRMIN. And it logs history by default, just like IRMIN. So you can kind of see where we're going with this, right? A lot of the components we built in the Mirage project are really kind of aimed at what the XenStore operation does by default. Now, there's one other thing in XenStore that causes all of the pain, just literally a decade of pain, and this has been transactions. And so transactions, so I've been, like James, I've been with the Xen project for quite a long time, and the original plan in 2002 was that this little daemon that we'd build would be the basis for a distribution. So the XenStore was originally meant to be distributed. It all went horribly wrong with the first implementation, the reason for this is that the transaction semantics are very, very hard to implement in an efficient way. And so why is this? Well, the problem is that there's a terrible performance impact from the way transactions work. So whenever you boot a virtual machine, any transaction involves almost hundreds of RPCs going back and forth between the virtual machine, DOM0, sometimes a domain builder, depending on how things are set up. And if any one of those operations causes a conflict, well, then you've got to abort and retry the entire set of operations. And so the longer lived operations are hugely penalized. This is the operations that you're trying to, you really want to succeed. And this means that short transactions can basically starve out very complicated long-lived transactions and just result in live lock. And so if you, for example, were crazy enough to start lots of VMs in parallel and it took 4 days, this is because there's lots and lots of transactions being attempted and merged and pulled back, and you're just burning vast amounts of CPU time. And as a developer community, we spent a lot of time trying to remove transactions from all parts of the tool stack as a result of this kind of crippling performance impact. Xend is legendary in terms of having a ton of transactions, and Ewan Meller spent 2.5 years trying to get rid of them, then realized we needed them, and they came back, and we've been flip-flopping, and then Xend got rewritten. So it's a bit of a sad story of conflicts and trying to get rid of them. And in fact, I'd argue that these transactions and conflicts are so devastating that they've really been hampering the scalability and the development of Xen as an entire hypervisor ecosystem. And no matter how hard we try to avoid them, though, they're not going away. So we do need to just figure out how to fix this stuff and kind of move on and start doing the interesting things. So luckily, though, it's not all doom. We do have an answer. And the observation is that a typical XenStore transactions, like creating domains, for example, in fact, fundamentally don't really conflict. It's just a flawed merging algorithm that doesn't recognize that it can just fix up a transaction very easily and make it simple to launch them. So if we were hypothetically, for example, managing these domain configurations in Git, we already have a set of operations we use in source code to deal with exactly this situation. We have the merge operations and the rebase operations to replay a set of operations as if there was no merge point. And so we've actually built a XenStore that replaces a lot of the OCaml baseline code and replaces it with a use of IRMIN. So we've just taken away maybe 60 to 70% of a lot of the logic in XenStore, replaced it with this IRMIN database, and actually just built the merge logic in a very, very simple bit of straight-line OCaml code. So this OCaml code, for example, attempts to merge, and then if the merge fails, it rebases, and then otherwise it puts a conflict through. So the amount of logic left in XenStore is just the Xen-specific bits, and all of the generalized stuff is all pulled out in this much more reusable library database called IRMIN. So just to give you a sense of performance, what happened here is that we have three things. We have the venerable C XenStore, and on the x-axis we have the number of parallel virtual machine starts and stops, and up there we have the actual total amount of time it takes. And you can see that there's an asymptotic difference in 3 implementations. The C XenStore just backs off like crazy. I think it literally copies its entire database every time it starts a transaction, so it's known to be very, very slow. In about 2008, we replaced it with the initial OCaml XenStore. And this was an interesting, it did a whole bunch of optimizations to make transactions more efficient, but it still has a number of conflicts. So now, with the new IRMIN-based XenStore, it needs a name, call it IRMINStore or something. It is much more efficient and there's almost no conflicts. So we're seeing that we're almost hitting linear start time for virtual machines. There's still a little bit of superlinear activity, but in general, we've managed to get conflicts under control and actually pull this off. So one of the interesting observations is that we've had to undo about a decade's worth of backpedaling. Because big transactions are really useful for a number of things. In particular, they give your database a notion of high-level intent, which is say that I want to start and do the sequence of operations and ensure they all happen in some atomic manner. And the fact that we decompose our tool stack into lots of small operations has been very harmful in terms of helping us to do this optimization. But once you restore these big transactions, now that we have a database that supports it, we get some incredibly cool new features. So, but the nice thing is that we can we put the big transactions back, and it's very useful for debugging and tracing what's going on within Xen. It gives us probe points very deep into the system. And we can also minimize just backend I/O, so we can just minimize the amount of actual activity. But we can also use this to build a completely fault-tolerant XenStore that can survive host reboots as well. So I'm just going to show you through some of the features now. But solving these performance problems gives us the ability to do debug tracing, minimizes a whole bunch of I/O, and it gives us fault tolerance in XenStore. So let's take a quick look at these features. So what happens if XenStore crashes right now? Well, in general, when XenStore crashes, you're just left with chaos in your system because it is the coordination engine for the entire host. So if you have hundreds of virtual machines, or in Felipe's case, 10,000s, then you're left with a lot of rings full of partially read and written packets. And so this is a bunch of state that we have to somehow recover. And there's no reconnection protocol in common use. There's been a bunch of patches, but we're always hampered by the fact that it'll be years before all of the kernels adopted and we can actually rely on the existence of a reconnection protocol. So instead, what we do is in the XenStore, we also have, in addition to the partially read rings, we also have per connection state. So every virtual machine has a bunch of stuff that it needs to know something about. And right now, the story for XenStore reliability is if it crashes, reboot the host. It's the only real way to get around the problem. So luckily, IRMIN to the rescue. Because it has a whole bunch of data structures that we've rewritten XenStore with, we can actually rebuild a lot of the interaction mechanisms it has with the host by using these persistent data structures. And so this means, in particular, for example, all of the per connection state just turns into a queue that is written into a Git-style database. And we can use these for watch events, so we can keep track of what's going on. We can actually persist the entire contents of the ring, which is just a relatively small structure, again into a Git-like queue. And then every time we restart, we can replay all of the things we had done on the ring and just recover what's going on. And we can also persist all of the connection information and replay them whenever we restart, so that we come back to the state that we expected. And one of the really nice things is that because all of this is in Git, we can actually introspect the state from within XenStore by just walking over our trees. And I'll show you exactly what I'm talking about in a demo shortly. Now, the thing with XenStore is that it's just incredibly hard to figure out what's going on sometimes. So as we probably noticed, is if you're trying to launch 10,000 VMs, everyone has a little solution for how we can fix the scalability problems in Xen. But really what happens is that you just look at these XenStore logs, you try to piece together a whole bunch of RPCs, and you can slowly deduce what happened. This is a typical way to debug a distributed system. The thing is, in real distributed systems, we typically have tools like Google's Dapper or Twitter's Zipkin to pull together traces of what's been going on, but we just didn't have anything like that in XenStore. So now with IRMIN and XenStore, we can simply git check out a copy of the database to a revision. We can inspect the state with ls, just using our normal command line tools. And the thing we're working on now is to git bisect any kind of automation. So we can say just revert back to your XenStore, automate a shell script so you can figure out exactly what the working and the bad states were, and just go back to exactly the point when the problem happened. So this is something that will hopefully be integrated into the Xen open source test tools, for example, and just give us back a reliable backtrace of the point we were in when something went wrong. And to give you a sense of what it looks like, this is I'll show you a live demo shortly. Hopefully I don't have net access, of course, but I'll see if I can get it to work. But you can just use Git, and it'll show you all of the merge and the nice trees and so on quite naturally. So the other thing is that where do we go from here? What is the future of XenStore? And the other thing that people do in XenStore, and it's almost always a bad idea, is to store large amounts of data inside XenStore directly. XenStore contains VM metadata, and then it also contains domain metadata about the actual the local Xen state of the particular host. So the problem is this virtual machine metadata is duplicated all over the place. So because the XenStore was never scalable enough, it resulted in a whole bunch of other tool stacks being built. For example, the Zappy tool stack, and to some extent the Excel config files, OpenStack's kind of metadata information. And there's just a ton of these things now that don't use the fundamental data storage mechanisms under the hood. And so if XenStore can store and distribute this data efficiently, then we can collapse a whole bunch of these things that are always out of sync and try to end up with one system that can actually manage all of the data for a cluster much more efficiently than you could otherwise. So again, we're hoping IRMIN to the rescue. One thing that the database can do is that you can check in all of the VM metadata into IRMIN directly. And because it's just using Git, you can just pull, push, and clone and use all of the usual ways to coordinate Git trees between hosts. You can even just push this stuff to GitHub. It does support the protocol. It's a little bit, obviously, non-human readable. It's all X expressions, but it works just fine. So you can actually just snapshot your cluster just by using the normal protocols we use for source code. The other thing that we've got that wasn't quite ready to demo, but it's very, very close, is that we can expose any kind of snapshot of XenStore to the host using Fuse. So we anticipate that we can actually just expose control connections. So you can say echo start to this particular UID inside XenStore and have it just do the right operation you want. So this makes it very easy to shell script and to do bits of coordination through normal file system interfaces. So the presence of XenStore as a file system that you can't actually mount as a file system for some reason is hopefully at an end. So instead of having all these custom binaries like XenStore LS and so on, you can just use the normal host tools to make this work. So again, it's just simplifying and making Xen a bit more integrated with the host. And finally, from a Mirage perspective, this is crucially important because we don't have a file system in Mirage. So the virtual machine data itself could be checked into XenStore, and thereby eliminating the need to have lots and lots of block devices for relatively small configuration files and so on. And so this is something that we're exploring more and more, particularly in the context of ARM devices, where we want to minimize the amount of management of all of these unikernels and just use one tool stack to persist the data where at all possible. So this is a lot of stuff, and which is why it's been taking quite a long time to pull together. But we do have lots of advanced prototypes of this that can boot virtual machines now, and using a lot of the existing Mirage libraries, but don't fully pass the unit test suite. And this is the problem with evolving anything to do with XenStore, is that there's a whole bunch of very obscure client-side bugs and so on that you just have to deal with. So the nice thing about the current architecture is that the core of the system is a very easy to understand Git style bunch of queues and merges and pulls and pushes, and then all of the weird Xen bits are in a separate module, so you can look at the quirks in the system. So in the future, if we wanted to, for example, move away from the binary protocol and replace it with a simpler one like protobuf or something, we can do that. But of course, we need some probing mechanism. And if we just want to remove some of the semantics, such as weird transaction semantics, then we can just do that for a particular set of new operating systems, for example, for MiniOS operating systems. So this makes it much, much easier to pull off. We have to write something which is quite important before we try to upstream this, which is to have a constant-sized database. Because obviously it's fine to have all of the history being recorded, but we do need some policy to rebase, for example, once every few weeks or whatever, just to make sure that the actual database on disk is constant size. So you might discard history and compress a whole bunch of redundant information over time. And finally, one massive benefit of doing these upstreaming is that it'll bring the Xen OXenstored back into the modern development stream of OCaml code. So we can use our modern package manager. We can use lots of libraries that use more scalable APIs. For example, the LWT threading library uses epoll and so on just to make code generally faster. And we can also make reproducible builds much easier upstream when using Xen Unstable. And from the Zappy project, the perspective is that we can remove a vast amount of database code from that part of the tool stack and just replace it with the new XenStore. So it'll generally simplify and bring these projects together. If anyone wants code, now I'm not going to obviously go through this, but if you look at the slide decks online, just go to dex.openmirage.org. One of the cool things about XenStore, it no longer depends on Xen, so you can actually do development in Mac OS X, which is very convenient for debugging the high-level protocols. And I can just show you a demo now as well. So let's see if I can get this to work without net access. So, this is the QB board, if anyone wants to see this. So this is where the slides have been running. It is an ARM, and you can XL list. Oops, I can sudo XL list, and you can see the decks, which is the actual slide decks that I've been presenting are just running as a virtual machine there. So what I'll do now is that I'm going to start a copy of the new XenStore on the system, and this is just obviously a development version. So the idea is I enable Unix mode, I run the database in a particular path, and I just get that to work. And this is the user space XenStore working. So then what I'll do is I will cd to the database, and I will start watching the Git tree. So this is just the command line I ran there is just running git log --1 line. It's there's no custom code here. It's just the standard Xen front end. Then I will start launching lots of virtual machines. And so at this point, you can see that you can just use the Git tracking to figure out exactly what's going on. The benchmark thing is creating lots and lots of domains, is pretending to be a parallel virtual machine start, and at the end of it all, you can just let me just start a lot more virtual machines. You can figure exactly what's been happening just by using the Git tools in the front end. Now this system is committing every single transaction into disk, but if you want to run this at scale, then you can actually use this to persist entirely in memory and decide when to commit it to disk. So you can have massively scalable Xen stores that run from this. So the implications of this is that it now gives us the ability to build a Xen store that can not only run inside a stub domain, but it can also naturally distribute itself. And this is going to be the ultimate answer to massive Xen store scalability. Because ultimately, you can build the ultimate C++ assembly language Xen store that's been optimized for speed, but it's only going to give you serial performance. But whereas if we want to scale across these many core NUMA nodes, I've got a 48 core machine here, same as the NEC folks, then we really want to make sure that we're maintaining NUMA affinity and generally following the bounds of the hardware. And to do that, it means we're going to run multiple XenStoreDs in separate stub domains, in separate NUMA domains, all coordinating and making sure that they take care of their patch of the memory. And so distribution is going to be one of the most exciting and hopefully not too dangerous parts of the new XenStore system. But it does open the path for managing all the metadata of hosts across a cluster, and also, for example, restoring a physical host in exactly the same state it was, or as close as you can get by restoring the XenStore entries that were in that previous host as well. So lots and lots of information about some of this stuff online. For the Mirage 2.0 release, we were driven by Lars to write lots of blog posts about what's going on, and it was very successful. So, and in fact, two of our interns from OPW and GSOC, Mindy and Josna, who are here, hopefully, they might not be at this talk. Oh, they're there? Wow, thank you for attending my talk. They will be at the panel tomorrow as well, and they've got blog posts online as well about testing various aspects of Mirage, and also to do better integration with Amazon EC2. And specifically, there's two posts about IRMIN and XenStore down there, which give you a much more detailed view of the database than we have here. And of course, IRMIN itself is independent of Xen, so you can use it for building all kinds of distributed systems as well. So we're using it to build lots of custom systems in ARM and building control systems and so on at the moment. So it's kind of an interesting way to take that logic and move it somewhere else. And with that, I think I'll take questions or confusion, depending on how they went. Hello. Hello, James.
So, since I asked Felipe earlier on, you've got quite a few XenStoreDs already.
Yep.
I think there's now 4 of that can count, correct me, no camel.
Yeah.
Can we coalesce these?
Yeah, no, this one is the coalesce one. So there's one mainline OCaml XenStoreD. As far as I know, there's only ever been 2 distinct OCaml XenStoreDs. One was written by UBC to experiment with the Remus fault tolerance system, and this one. So this one is just an evolution of the XenStoreD currently in trunk. Yeah. See, I don't think we pretty. The problem is no one wants to maintain XenStoreD, but someone has to. It's just that there's a ton of corner cases in XenStoreD that you have to deal with, and the UBC one it just never quite landed in the fire.
So where is the canonical location, upstream project-wise, for OCaml XenStore?
Oh, it's GitHub Mirage. It's right here. Oh, well, to upstream this though, we're going to submit patches that will remove the one in tree, but it's not clear it's the right thing to do for 4.5, because we want to do this early in the release cycle, so probably for 4.6 after a nice Christmas we will. Oh, absolutely, yeah. And then we'll fork it again. That's right. No. This one will be, but there's a ton of benchmarking to do and memory usage and stuff to make sure this one is no worse. Yeah, there's a big one as well. So yeah, don't worry, we're gonna have one XenStoreD. We have to rename it though because it doesn't depend on Xen anymore. So if anyone has any ideas for cool names, XenStoreD is kind of a boring name. It needs to change. Sorry.
Can you talk a little bit about why transactions are needed in this? What it's exactly behind it?
Right. So there's so the reason for the RPC is that you have a whole bunch of backend domains that are dealing with physical device setup. So in Linux, for example, if I'm setting up a virtual machine and it decides to hot plug a virtual network device, then something in the backend needs to set up all the bridging scripts and so on to make sure that works. And this is true for all of the split drivers in Xen. So I think there's about 14 different PV protocols for front and back end now, things like SCSI and USB and so on. And so for each of those, there typically needs to be some kind of a serialization protocol to make sure that 2 concurrent requests don't do the wrong thing. And in particular, things like ID generation and triggering off asynchronous scripts and so on. If any of those fail, you want to undo all of the side effects that happened throughout the network device setup. And so the purpose of transactions is to make sure that you can do a sequence of RPCs back and forth, and if anything goes wrong, everything will be undone at any given time. So it doesn't have to be transactions. You could have some kind of a tracking system that would guarantee would undo everything. But transactions were what were decided in the Castle pub in 2003. I'm not even kidding. And this is.
There's a lot of wisdom coming from there, but
There's a lot of wisdom that is a very bad idea, I think, but it's what we have right now. The new XenStore does give us a basis from which to remove these transactions, because one of the interesting things about using Git is that while the transactions are present in the merge, afterwards there's no hint of the transactions. You just see the actual stream of operations. So we could start evolving away from transactions, but we'd have to modify all the front-end drivers in Linux, the BSDs, Windows, PV drivers, and because it's baked into the protocol. And
but you could, in principle, sort of associate IDs with these sequences of things and say, oh, this is ID 15 or whatever, and it does a sequence and deal with that. I mean,
Right.
operating systems and whatever don't typically have transactions internally to support this. So I'm just
well,
trying to get my head wrapped around exactly.
Well, so
whether this was a good idea or a bad idea.
There is one feature
what the trade-offs are.
right. So there is one feature that allows which you can't do in a normal operating system. So in a normal operating system, you have two parties. You have the kernel and you have user space. Here, though, you can have untrusted third-party driver domains that drop into the mix. So if I'm setting up a front-end network driver in a virtual machine, then the back-end network card could be run in a domain that is not domain 0. And so at this point, you have three domains that don't really trust each other, all trying to coordinate. And so it's very hard to generate unique numbers and form a consensus protocol. You're basically building something like Paxos. And so transactions are the simplest way to make sure that given this group of things, you give it to someone else and everyone commits them in one go. And it's a very well understood something from databases. But if you're going to take something from the database community, then we should build a database, right? We shouldn't try to approximate transactions through just a very kind of limited bit of code. So in the new XenStore, we should be able to build a query interface, for example, for what Felipe wants for not linearly scanning the entire database to get a key. That's actually a very simple thing to maintain in this kind of Git-style model. You can build a NoSQL set of indices quite trivially. But for transactions, though, the fact that we have a multi-party system makes it almost, it's very hard to do things like just global ID generation without having the trust of the other nodes in the system. That's the fundamental difference. And I think a few people have tried. There was an attempt in 2005, I think, to do this by having a bunch of tokens, capabilities that would be passed around, and it became very, very slow because you'd have to pass the capability to the next virtual machine that would be dealing with the next part of the sequence, and you just couldn't parallelize anything. Here, everything can be done in parallel. The front end, the back end setups, and no one observes the differences. Despite the criticism, it's actually a very solid bit of code, but it's just very complicated.
We are technically into the break time now.
Right.
And you have a block?
Oh, yeah, I guess we do have a block. Yes, with Adam. We're going to do chat unikernels and stuff, HalVM, OSV. I don't know if anyone from Erlang and Xen is here, and Mirage, of course, in that room over there. We're going to try to get this ARM stuff working. So.
Okay, well, first off, let's just give him a hand for a great job.
Thank you.